Our next speaker is Eliezer Yudkowsky. He's one of my colleagues at the Singularity Institute. He's one of the co-founders and research fellow. He's going to be talking a little bit about the different schools of thought around this notion of the singularity. And Eliezer is probably most well known for a lot of the research he's been doing on what he calls friendly AI. Essentially, how do you work out the theory, the math behind ensuring that you can create a self-improving system that can go through many iterations of improvement in its goal system and actually maintain the original intended goals of that system without it changing what it does, over a future either billion iterations or however many you want to consider. There are a lot of complex mathematical issues involved in this, and he wrote a paper in 2001 called Creating Friendly AI, the Analysis and Design of Benevolent Goal Architectures. So he'll be talking about that tomorrow, but right now he'll be just focusing on the singularity, and he's getting set up here, so just be a few minutes.
Good morning. Am I on? So I'm Eliezer Yudkowsky, a co-founder and current research fellow of the Singularity Institute for Artificial Intelligence. Here to deliver a quick introduction to the singularity and three major schools of thought that have popped up. Back when the Singularity Institute was first starting up, the word singularity got used a lot less often than it does now, and it means a sort of different thing today than it does when the Singularity Institute got started. There's three major schools of thought that have become associated with the word. One that you've all heard of already, I'm sure, is Ray Kurzweil's accelerating change. There's also Vernor Vinge's event horizon and I.J. Good's intelligence explosion. I'll start off with accelerating change. Stripped down to its core essentials, accelerating change thesis is that human intuitions about the future are linear, but technology change feeds on itself and therefore accelerates. People instinctively expect around as much change in the future as they've seen in the past, if not less. But technological progress feeds on itself. The more we learn, the more we learn. So the future will contain more technological change than people expect. There's also a bolder version of accelerating change, which says that technology change is smoothly exponential, so we can predict the date when new technologies will arrive. These are the manifold variations of Moore's law for the speed of the fastest supercomputers, transistors per square centimeter, operations per second per $1,000, all doubling every year or 2 years or 18 months. Here we see a graph of the fully generic version of Moore's law, which shows techno-juju increasing exponentially over time. As you can see, the amount of techno-juju we have is going up by a factor of 1,000 every 15 years. If we extrapolate this trend into the future, what do we get? That's right, big juju. As you can see from this graph, we're going to cross the threshold of big juju in 2031 on April 27th between 4 and 4:30 in the morning. Now, not even the bold claim is actually that bold, of course. The real argument goes something like this. If you look back at the rise of the internet from the perspective of the man on the street, the internet blew up out of nowhere. There's a sudden huge spike in the number of internet users on a linear graph. On a logarithmic graph, the increase looks much more steady. So an accelerationist would say, there's no use in acting all surprised by your business model blowing up. You had plenty of warning. The core thesis of accelerationism is that huge changes are coming larger than you'd expect from linear thinking, and the bold thesis is that you can actually time the breakthroughs. Criticisms of the bold thesis don't necessarily hit the core thesis. Computing progress could be only roughly exponential. Too bumpy to predict exactly, but roughly exponential progress still means you're going to get hit with huge changes somewhere down the line. Any positive second derivative implies future changes larger than past changes. So criticizing Moore's law is not a knockdown argument against accelerating change. And now for something completely different. The event horizon, which is what Vernor Vinge originally named the singularity back in the 1970s. Sometime in the future, technology will advance to the point of creating minds that are smarter than human through brain-computer interfaces or purely biological neurohackery or by constructing a true artificial intelligence. Werner Vinge was a professor of mathematics who also wrote science fiction, and he realized he was having trouble writing stories set in a future past the point where technology creates smarter-than-human minds, because he was having to try to write characters who were smarter than he was. And at that point, his crystal ball cracked through the center. This is why Werner Vinge originally called it the Singularity, after the center of a black hole where 1970s models of the laws of physics broke down. Note that it's the model of the future that breaks down, not necessarily the future itself. If I am ignorant about a phenomenon, that is a fact about my own state of mind, not a fact about the phenomenon itself. Something happens, we just don't know what it is. Stripped to its bare essentials, the core thesis of the event horizon is that smarter-than-human minds imply a weirder future than flying cars and amazing gadgets with lots of blinking lights. Imagine, if you like, that future technology finally produces the personal jetpack that lets you fly all around the city. Well, birds flew before humans did, but they didn't take over the world. The rise of the human species did not occur through flapping our arms. In our skulls, we each carry 3 pounds of slimy, wet gray stuff corrugated like crumpled paper. The brain doesn't look anywhere near as impressive as it is. It doesn't look big, or dangerous, or even beautiful. But a skyscraper, a sword, a crown, a gun, all these popped out of the brain like a jack from a Jack-in-the-Box. A space shuttle is an impressive trick. A nuclear weapon is an impressive trick, but not as impressive as the master trick, the brain trick, the trick that does all other tricks at the same time. Usually when you say intelligence, people think of book smarts, like doing calculus. Success in the human world takes more than book smarts. There's also persuasiveness, enthusiasm, empathy, strategic thinking, musical talent, rationality, thinking on your feet. But notice that every factor I just listed is cognitive. Political strategizing happens in the brain, not the kidneys. You won't find many famous politicians or military generals who are monkeys. Intelligence, you might say, is the foundation of human power. It's the strength that fuels all our other arts. In everyday life, people think about the scale of intelligent minds as if it ran from village idiot to Einstein. But this is a range within humans who are themselves the smartest creatures on the planet. If you can take an IQ test designed for humans, you've already established yourself as a member of the cognitive elite no matter what you score, because a mouse would just eat the IQ test. So when I talk about intelligence, I'm talking about the trans-species scale, the scale that starts with a rock at 0 intelligence and runs from there to flatworms, to insects, to lizards, to mice, to chimpanzees, to humans. At the core, Vinge's event horizon is about intelligence. Improving the brain is a very serious business. It tampers with the roots of the technology tree, goes back to the cause of all technology. And that makes the future a lot stranger than strapping on a jetpack. If you want to know the true shape of the future, don't be distracted by amazing gadgets with lots of blinking lights. Look to the cognitive technologies, the technologies that impact upon the mind. The bolder thesis of the event horizon, the stronger claim, is that to predict anything a transhuman mind would do, we would have to be at least that smart ourselves. If this is true, the future becomes absolutely predictable and our models absolutely unpredictable, and our models break down entirely. Now, you might ask, if the future beyond the event horizon is absolutely unpredictable, or even just really weird because there are transhuman minds around, could we still predict that Moore's law would continue at the current pace? Here we see the shadowed graph of Moore's law. The increase of techno-juju continues at the current pace until we have enough techno-juju to create smarter-than-human minds, and then we don't know what happens after that. So the event horizon thesis tends to argue against the bold thesis of accelerating change. We can't predict the future precisely, but via smooth exponential graphs. But the core thesis of accelerationism is just that future changes will be greater than past changes because technological change feeds upon itself. And that, the event horizon thesis definitely supports. So the event horizon supports the core thesis of accelerationism, but argues against the bold thesis. And this is why it's important to disentangle all these concepts. Another disentanglement, the event horizon does not require accelerating change, and especially not bold accelerationism. We could reach the threshold level of technojuju to create transhuman intelligence by following the previous historical line, as shown here, and as the bold thesis of accelerationism implies, or we could reach the threshold by following a different line, a rougher line, one that proceeds faster or slower than history would lead us to expect. We could reach the threshold following some totally weird trajectory that dips down and comes back. So long as you eventually get enough technology, you eventually get artificial intelligence or brain-computer interfaces or neurotechnology, and then the crystal ball cracks. So the event horizon does not require accelerating change, and a devastating criticism of Moore's law may not be a devastating criticism of Werner Vinge's original singularity thesis, which I've been calling the event horizon. The third school of singularity thought is the intelligence explosion, which goes back to the 1960s and was invented by the famous Bayesian mathematician I.J. Good, and also pre-invented in the 1930s by the science fiction editor John Campbell. Mind has always been the source of technology. All the changes that occurred over the last 10,000 years were produced by constant human brains. 10,000 years ago, as today, our ancestors had a prefrontal cortex, visual cortex, limbic system, the same brain architecture as today. But now we're talking about using technology to improve intelligence, and that closes the loop. Suppose you had humans with brain-computer interfaces that augmented their intelligence. What might they do with their augmented intelligence? Play the stock market? Cure cancer? One good bet is that they would use their augmented minds to design the next generation of brain-computer interfaces. The smarter you are, the more intelligence you have at your disposal to make yourself even smarter. Minds making technology to improve minds is a positive feedback cycle. And this, stripped down to its bare essentials, is the core thesis of the intelligence explosion, that intelligence enhancement is a tipping point, like a triangle balanced on one corner. Once it tilts over even a little, gravity pulls it down the rest of the way. The most extreme version of this thesis is an artificial intelligence improving its own source code. If you try to do intelligence enhancement by genetic engineering, then it takes 18 years for the kids to grow up and help engineer the next generation. For humans with brain-computer interfaces to design the next generation of brain-computer interfaces might take 18 months. For an AI to rewrite its own source code might be 18 seconds. It's when we start talking about artificial intelligence that we start to see how large the intelligence explosion might be. Even if you consider only the hardware of the human brain, as opposed to the software, you can see plenty of room for improvement. Human neurons spike an average of 20 times per second, and the fastest recorded neurons in biology spike 1,000 times per second, which is still less than a millionth of what a modern computer chip does. Similarly, neural axons transmit signals at less than 150 meters per second. 1 meter per second is more usual, and that's less than a millionth the speed of light. So it should be physically possible to have a brain that thinks at 1 million times the speed a human does, without even shrinking it or cooling it. At that rate, you could do 1 year's worth of thinking every 31 physical seconds. So I should emphasize that this in particular is more of a thought experiment than a prediction. The main reason for discussing this is to illustrate that the human mind is not an upper bound. Just as a skyscraper is orders of magnitude taller than a human, and a jet plane travels orders of magnitude faster than a human, you can have minds that think orders of magnitude faster or have orders of magnitude more computing power. There is nothing in the laws of physics against it. Okay, so one widespread criticism is that we should not worry about any of this because AI has failed to make progress over the last few decades. Yes, I hear this a lot. Very amusing. It seems like all known AIs today are dumber than a village idiot. And this is true. If you use the within human scale of intelligence to look at AIs, then AIs today are dumber than the dumbest humans, just like every other animal on the planet. And AIs have been dumber than a village idiot for quite some time now, so it's clear that AI has failed to make progress. But you shouldn't use the human scale of intelligence to judge AIs. It appears to me that AI has come quite a long way, that we have been creeping up the scale, though slowly, but to a human it all falls off the cliff of the human scale and becomes dumber than a village idiot. And plus, of course, as soon as Rodney Brooks does something impressive, it's not AI anymore. So strictly steady progress in artificial intelligence from a human perspective might look something like this. And that is not even taking recursive self-improvement or the intelligence explosion thesis into account. There's no threshold in that diagram where the human programmers stop improving the AI from the outside and the AI starts improving itself from the inside. If an AI is thinking 1,000 times as fast as human programmers, shouldn't it improve itself faster than humans tinkering from outside? So maybe what we ought to see is something like this. And that may seem a bit silly, but if you were to look at the graph of, say, how much complexity there was on Earth, the graph would look a lot like that, starting with the invention of human intelligence. So if you think of that as an economic sort of graph, like what does the global economy look like once human intelligence comes along, it would probably look remarkably like that. This sort of thing is not unprecedented, it's just very impressive. So the bold claim of the intelligence explosion is minds making technology to improve minds is a positive feedback cycle which, once it gets started, rapidly surges upward and creates superintelligence. This sort of thing is the argument for why it would not be a good idea to wait until after we have human-level AI before we start thinking about the implications of the technology, and in particular about transhuman AI. So if we put the bold claim of the intelligence explosion on a Moore's law graph, it might look something like this. Note that this graph contradicts both strong accelerationism, because change isn't accelerating at a smooth pace, and also contradicts the strong event horizon, because we're making a prediction about what happens after the singularity. And one often hears, well, there are physical limits to computation, so this can't continue forever. Well, according to our current models of physics, there are physical limits, but they're way the heck off the top of this graph. It's way above the ceiling, I think, even. So another important point about this graph of the intelligence explosion is, what does that blue line represent? In the intelligence explosion, the key threshold is criticality of recursive self-improvement. It's not enough to have an AI that improves itself a little. It has to be able to improve itself enough to significantly increase its ability to make further self-improvements, which sounds to me like a software issue, not a hardware issue. So there's the question of, can you predict that threshold using Moore's law at all? Which in turn brings up the issue of trying to calculate the arrival time of the singularity, which is a popular pastime among accelerationists. So let's go back to the event horizon graph. By far the most popular method for trying to time the singularity is to look at the brain, try to calculate how many operations per second it does, and then project Moore's law out to calculate when we'll have that much computing power. But this does not take into account the question of software. Jordy Rose of D-Wave Systems recently was kind enough to provide us with a startling illustration of software progress versus hardware progress. Suppose you want to factor a 75-digit number. Would you rather have a 2007 supercomputer, IBM's Blue Gene L, running an algorithm from 1977, or a 1977 computer, an Apple II, running a 2007 algorithm? And Jordy Rose calculated that Blue Gene L with 1977's algorithm would take 10 years, and an Apple II with 2007's algorithm would take 3 years. In artificial intelligence, this sort of thing is harder to calculate and graph. AI breakthroughs usually let you do things that previously would have been outright impossible because you just had no clue how to do them. But I'll say that on anything except a very easy AI problem, I'd much rather have modern theory and an Apple II than 1970s theory and Blue Gene. Each conceptual breakthrough in AI drops the computing power necessary to achieve AI. At some point, you get enough computing power to cross the current threshold, or you get one last theoretical breakthrough that crosses your current threshold of computing power, and that, perhaps, is when you get true AI. Or you might say that brute force, more computing power, more brute force, lets you get away with a less clever design. But if you don't know what you're doing, if you fundamentally just have no clue how to build a mind, then all the computing power in the world may not help you. Or another way of seeing this graph is as an extension of Moore's law of mad science. Every 18 months, the minimum IQ to destroy the world drops by 1 point. So from the perspective of the intelligence explosion school, the critical threshold may have nothing to do with human equivalence per se, because humans don't rewrite their own source code. We're not trying to do something that is equivalent to something that humans do. You could get the intelligence explosion as the result of a theory breakthrough in self-modification, reflectivity, thinking about thought, and other things could fall out of that if the AI was smart enough to add them to itself. Oh, okay, so to sum up, the three schools' core theses are as follows. Accelerating change. Intuitive futurism is linear, but technology change accelerates. Event horizon. Transhuman minds imply a weirder future than flying cars and gadgetry. Intelligence explosion. Minds making technology to improve minds is a positive feedback cycle. So the three schools of thought are logically distinct, but can support or contradict each other's core or bold claims. The core theses all support each other. They don't necessarily imply each other or logically require each other, but they support each other. And I fear that is why the event horizon, the intelligence explosion, and accelerating change are often mashed together into singularity paste. These three schools did not always exist. There may be room for a fourth school. I personally do not like usages that widen the singularity term too much, make it too generic, or just say, well, there's some kind of unspecified big event in the future. This is where you get the sort of bloggers who read one post about the singularity and go, haha, it's the nerdocalypse. They haven't found any substantive claims associated with any of the major schools or the lesser schools, that some of which may very well emerge here at this summit. But a new school should, these three schools all have substantive theses, interesting claims. You can distinguish their premises from their conclusions. A new school should make equally interesting claims. It should say, here's the premise, and here's what results from that. Here's why the premise is interesting. And if you give the singularity a new definition, as I'm sure many people will do at this summit, I would ask that you please, for the love of cute kittens, tell us exactly what you mean by the word. And this has been Eliezer Yudkowsky for the Singularity Institute for Artificial Intelligence.
Raise your hand, or ideally go up to a mic. You got any questions, anybody? There's one.
Multiple processors, software defined, how are we going to make that leap? What's going to make the software be able to deal with all those processing cores to give us some advantage?
So the question was, how are you going to make the leap to using multiple processing cores? And well, there's probably people who will be speaking who know a bit more about that than I do. I mean, I've been going around saying it is not about brute force, that the true way of AI is as pure as the moonlight reflected from a pool of still water. So you shouldn't so if you are following the true way, then you should not need all that much computing power, though of course it is always fun and helpful to have. It's just the notion of throwing brute force at the problem that I object to. My guess is that there's all different kinds of AI algorithms, and parallelizing some of them will be more work than others. There's not going to be a magic bullet for it, but nonetheless, AI does tend to be a bit more parallelizable than most ordinary computer programs, though it does depend on the algorithm. That would be a question for tomorrow's talk, I think, actually.
It sounds like there's a large mechanistic thrust to this. I'm wondering what is the biomimetic or even nanobiomimic, what's the wet side of the singularity, or is there one? Is there biology and evolutionary theory, the stuff that got us here? How does that contribute to this?
There's certainly a possible set of paths to the singularity that involve brain-computer interfaces or hacking the brain. It's not actually my own specialty, so maybe I don't talk as much about that as I should. I personally tend to be sort of skeptical because the first heavier-than-air flying machine was neither an artificial nor a scaled-up bird. And I do think that despite the seeming incredible difficulty of starting over from scratch, it is easier in the end. That once we know what we're doing, it will be easier to make it from scratch than to hack with the existing enormous mess of spaghetti code that is the undocumented, non-end-user modifiable human brain.
Eliezer, will tomorrow's segment include the relationships between technology and ethics?
I will be talking about ethics tomorrow. I don't know that I would see the relation of technology to ethics as a separate subject. Technology is a function of our existence as humans, and ethics is what guides our existence as humans, and therefore, there's a natural rather than a special joining between technology and ethics.
Eliezer, when people donate money to you, what do they want you to achieve? What are they hoping you'll accomplish? Do you see an accelerating increase in contributions or in investment in this area?
Well, the singularity, the question was, what do people donating money to the Singularity Institute expect the Singularity Institute to do, and have we been seeing an exponential increase in contributions? and we did actually receive more than twice as much in donations this year as last year, for which we may credit Tyler Emerson, and as well as our matching funders, Rob Zara, Peter Thiel, and Michael Vassar, who matched many donations. What do they expect us to do? Well, we're supposed to figure out how to build one of those intelligence explosion grenades and very carefully shape it to be friendly and pull the pin. That is the Singularity Institute's purpose.
Eliezer, you mentioned the intelligence explosion. It seems to be dependent upon the possibility of recursive self-improvement, which of course isn't yet possible for AI. Have you seen that phenomenon in other systems? Have you studied any other system that recursively self-improves?
I think the closest thing we've ever seen to a recursively self-improving system is the process of humans thinking about how to think and inventing science, which is a discovery about how to think about how to think. It's a extremely open problem, maybe the most important open problem in artificial intelligence. I don't think there's any real-world AI systems out there getting real-world mileage out of thinking about thinking at this present time, so it's a big puzzle. Okay, well, next question.
Okay, well, Dr. Canton actually made this point, so I want to elaborate on it. What's your thought about evolutionary computing? Forget wetware, but just in current-day models that use reconfigurable computing to emulate self-evolving systems. Where do you see that in your framework?
I'm actually a major skeptic about that, because the remarkable thing about evolution is not how well it works, but that it works at all. That you can actually get anything as complex as a butterfly out of a system with zero intelligence, just sort of stumbling around in the dark and moving on whenever it finds a tiny ray of light. Evolution requires hundreds of thousands of generations to create complex machinery that a human programmer can create in an afternoon.
But John Coase's department, his department chair at Stanford, he actually does this using millions of iterations in a very short amount of time. Just kind of wondering about that, what your thoughts are.
But it's still a brute force use of computing power. The human mind does it, I won't say elegantly because we are still a big mess, but vastly more efficiently than evolution. We do not need to create millions of tiny little iterations of our programs in order to just reach in and edit the darn code.
Would you ever have John Coase debate you on this? Just curious.
I would be happy to debate him if anyone asked me to do that, but I'm not sure we would. I don't know yet if we would actually have a disagreement. I mean, the fact that you can get enormous amounts of mileage out of something today doesn't mean that it is the path to human level and human plus AI.
Okay.
There's one down, front row. Front row, right there.
Do you think that we can, at this point, estimate just what the threshold for recursive self-improvement is and what the rate is, what the estimate is, and if so, how?
And repeat the question, Eliezer.
The question is, can we estimate the threshold for recursive self-improvement? And my answer is, I don't quite see how you could do that because you'd have to be I think you'd have to be measuring the time to a particular math breakthrough. But if anyone could graph that and measure it, it would be Ray Kurzweil.
I guess to simplify my question, what is the minimum amount of computing power you would need for a grenade?
An intelligence explosion grenade, not just a regular grenade. Regular grenades require very little computing power.
Say for Einstein.
I really think it depends on how clever you are about how you write the program. If I were to make a number up completely out of thin air without doing any calculations, which is therefore totally bogus and probably even more misleading than my just saying I don't know, I would guess that that a billion operations per second could do it if you were clever enough and had maybe like another 100 years worth of science before you started trying to program it. It will not be created on a billion operations per second, but my guess is that a human could do it with another 100 years worth of AI science.
My question has to do with the relationship between the binary approach to AI versus the cognitive. Early on, you brought up cognitive issues, and I'm wondering whether the programming of cognitive issues actually changes their identity and converts them into binary, and hence removes the human being from the situation.
Well, I think that might be a sort of question about the role of logic in artificial intelligence, and I think that artificial intelligence has come a long way from its logical days. Nowadays we have probabilities, and if anyone's interested, there's a really, truly wonderful book from 1987 called Probabilistic Reasoning in Intelligent Systems, Networks of Plausible Inference by Judea Pearl, which describes in some mathematical detail exactly what goes wrong if you try to use first-order logic to describe reality.
Thinking of an analogy with human agriculture for fertilizing various fruit plants, farmers using bees to grow species. It's pretty simple, but it's nonetheless an important link to that cycle making things happen. Now, software, the cycle that we have for improving software intelligence today has a human developer using exponentially improving tools to create software tools to create exponentially improving machines software. So I guess the question is, to the extent that you have that the machine, the software pieces of that become more and more important, and the human role becomes, let's say, more like the bees, sort of what makes that, and is that or is that not a legitimate scenario for saying, here's a cycle of machine self-improvement, essentially where the software is doing more and more of it, but you still have a role for that smart human.
I think that if one went that route of the AI getting smarter and smarter and the humans playing less and less of a role, there would be an increasing pressure to remove the human from the system in terms of efficiency. You might keep them around because you have some kind of notion of permissive action links or something like that. But in terms of efficiency, you'd have a core component that was increasingly a bottleneck. Imagine an AI that is thinking 1,000,000 times as fast as its operator. That operator is going to be slowing down the system by a factor of thousands or even 1,000,000 outright. So there's going to be a huge pressure to remove the slowest link in the system.
Okay, I think that's about it. Thank you, Eliezer.